Welcome to the sixth part of my video series on extinction events throughout Earth's history. Today, we're diving into the Triassic period, the dawn of the Mesozoic era. The Triassic was a turbulent time. Life was still reeling from the most devastating extinction event in Earth's history at the end of the Permian. But even as ecosystems began to recover, they were far from stable. This fragile balance between survival and collapse would be shattered again and again by a series of extinction events, culminating in the fourth largest mass extinction in our planet's past. If you're new to this series, don't worry, this video stands on its own, but if you're curious about earlier extinctions, check out my playlist for a deep dive into Earth's most catastrophic events. You'll find a document in the video description listing sources for images and research papers used in this video. Let's set the stage. Imagine a vast, dry supercontinent under a blazing sun. This was Pangaea, a single landmass surrounded by a global ocean. The Triassic period lasted from around 251 million years ago to 201 million years ago, and over those 50 million years, Pangaea slowly began to divide into two landmasses, Laurasia in the north and Gondwana in the south, a process that would continue into the Jurassic. The climate was hot and dry. Earth had emerged from the late Paleozoic Ice Age, and the poles, once frozen, now hosted temperate forests teeming with life. Closer to the equator, deserts dominated, though periodic rainfall offered brief windows of opportunity for ecosystems to flourish. We can break the Triassic climate into three distinct phases. The early Triassic was the hottest time in the entire Phanerozoic eon, thanks to enormous greenhouse gas emissions during the end Permian extinction. This time is known as the Permian-Triassic thermal maximum. The Middle Triassic was a time where the Earth started to cool, but it lasted only about 2 million years. Into the Late Triassic, the Earth continued to cool, but this was punctuated by renewed volcanic activity that caused additional global warming and associated mass extinctions. Marine ecosystems were radically transformed after the Permian extinction. Once dominant species vanished, replaced by new evolutionary experiments. For example, phytoplankton communities now included algae with red algal-derived plastids, a shift from the green and red algae that had dominated since around 650 million years ago. Corals began to return, forming small reef patches, a faint echo of earlier reef-building ages. Serpulids, a type of marine worm, appeared in the mid-Triassic. Shelled cephalopods, mostly ammonites, not only survived the end Permian extinction, but thrived and diversified. Bivalves flourished as well, spreading widely during the mid-Triassic. Fish remained relatively low in diversity, with a few genera found worldwide. Coelacanths, relics from the Devonian, had their most diverse showings since that time. Ray-finned fish became especially successful, peaking during the Middle Triassic, a trajectory that would continue into the modern era. Lungfish and sharks, too, found success in both marine and freshwater environments. On land, large amphibians called temnospondyls, once dominant, were in decline. Terrestrial forms were gone, only aquatic and semi-aquatic species persisted, and only the suborder Stereopspondyli managed to survive throughout the Triassic. The synapsids, once rulers of the Permian world, had been reduced to a few therapsid lineages, Dicynodonts, Therocephalians, and Cynodonts. The first two of these groups were prominent early in the Triassic, but were extinct by the end. The Cynodonts, however, endured, and from them, early mammalia forms arose. These small, likely nocturnal insectivores would eventually give rise to true mammals. Meanwhile, the reptiles were on the rise. The archosauromorphs, including early dinosaurs and pterosaurs, were emerging. Among them, the pseudotsuchians, ancestors of modern crocodiles, diversified into an astonishing array of terrestrial predators, herbivores, and omnivores. Long-legged and sometimes armoured, these reptiles filled niches across the landscape. In the oceans, reptiles were also taking over. By the late Triassic, the first turtles appeared. Earlier groups like nothosaurs, pachypleurosaurs, and thalattosaurs thrived. These strange herbivorous Atopodentultus emerged, as did the iconic marine reptiles, plesiosaurs and ichthyopterygians, both destined to dominate the Mesozoic seas. And let's not forget the insects. This was a key time in their evolution. During the Triassic, holometabolous insects, those with complete metamorphosis like flies, butterflies and beetles, began to diversify rapidly. Though they first appeared in the Carboniferous, it was in the Triassic that they became ecological powerhouses. Now that we understand the Triassic landscape, it's time to talk about extinction. Though shorter than previous geological periods, the Triassic saw multiple extinction events. Many were smaller and less studied, but still significant. The first of these wasn't far removed from the end Permian extinction itself. Just 500,000 years later, around 252 million years ago, Earth experienced the Griesbachian-Dienerian boundary event, time that has been described as the severest crisis overlooked. The earliest age of the Triassic is the Indian, further divided into two sub-ages, the Griesbachian and the Dienerian. This event marks the transition between them. This event primarily affected the flora. The dominant post-Permian survivors were gymnosperms, ancestors of modern conifers, cycads and ginkgos. But as the world cooled and became wetter, these drought-tolerant plants were gradually replaced by lycopsids, spore-bearing plants more suited to humid environments. Both groups of plants survive today, so this wasn't a true extinction, but rather a floral turnover to reflect the changing climate. It's a reminder that extinction doesn't always mean annihilation. Sometimes it's about shifting dominance, and in the Triassic, those shifts were just getting started. However, this dominance of lycopsids was short-lived. The flora quickly shifted back in favour of gymnosperms during the second major extinction event of the Triassic, the Smithian-Spathian extinction. Occurring around 249 million years ago, just 1 million years after the Griesbachian-Dienerian boundary event, this was another extinction that flew under the radar until relatively recently. First recognised in the 1990s, research into it has continued into the 2000s and beyond. These dramatic swings in dominant flora reflect the Earth's struggle to stabilise after the end Permian apocalypse. Shifting rainfall and temperature patterns favoured different plant groups over time. Sometimes lycopsids thrived, but for most of the period, gymnosperms held the upper hand. Although these floral changes were significant, the biggest impacts of this extinction were felt in the oceans. Ammonoids, conodonts, and radiolarians all suffered major losses in biodiversity. Ammonoids were particularly affected as many of their species were widespread, so their decline left a noticeable vacuum in marine ecosystems. Interestingly, this extinction event coincided with a sharp rise in marine reptile diversity, suggesting that their dominance may have been partly due to the ecological space left behind. During this time, the Earth experienced a sudden spike in global temperatures, briefly interrupting the overall cooling trend. This heatwave was followed by an equally sharp cooling. Mobile marine species retreated from the tropics during the temperature spike, but those unable to migrate faced harsh survival odds. Roughly 50% of bivalve species perished, and tropical land regions became nearly lifeless. Once the climate stabilized and cooled, animals began to return to the equatorial zones. So, what caused this rapid heat spike and the marine die-offs? The leading theory points again to volcanic activity in the Siberian traps, the same culprit behind the end Permian extinction. While these volcanoes had quieted down earlier in the Triassic, evidence suggests they reawakened, triggering the Smithian-Spathian crisis. Sea surface temperatures may have soared to around 40 degrees Celsius or 104 Fahrenheit, effectively cooking marine life. This was followed by a sharp drop of about 8 degrees Celsius. While extreme temperature shifts explain part of the devastation, they don't tell the whole story. Ocean acidification, widespread anoxia or lack of oxygen, and toxic chemical changes, possibly from mercury released during volcanism, likely played roles too. Though mercury levels were elevated, their timeline doesn't perfectly align with the extinction, suggesting they may have been a contributing stressor rather than the primary cause. Now we come to the third event in this rapid-fire sequence of early Triassic crises, the Olenkian-Anisian boundary event. This occurred around 247 million years ago, just 2 million years after the Smithian-Spathian extinction. Like the Griesbachian-Dienerian event, it's better described as a period of faunal turnover rather than a true mass extinction. As Earth's climate continued to shift, so too did its ecosystems. Species that had barely survived the end Permian extinction began to adapt, diversify, and evolve into new forms, helping to rebuild biodiversity across land and sea. In the oceans, this event marked the appearance and diversification of ichthyosaurs and plesiosaurs, two groups of marine reptiles that would go on to dominate Mesozoic seas. On land, the archosaurs continued their rise. Dinosaurs themselves wouldn't appear until a bit later, around 243 million years ago, but their roots trace back to this period of recovery. The Olenkian-Anisian boundary event was less of a sudden catastrophe and more of a slow transitional phase. It reflected ongoing environmental changes, shifting sea levels, fluctuating temperatures, and a gradual reduction in atmospheric greenhouse gases that created new opportunities for life to flourish again. After the rapid series of climatic shifts in the early Triassic, the Middle Triassic was relatively stable. This created a small gap between the Olenkian-Anisian boundary event and the next major extinction, the Carnian Pluvial episode, which occurred around 234 million years ago and lasted for 1 to 2 million years. The Carnian age of the late Triassic was typically dry. However, during the Carnian Pluvial episode, the Earth experienced a dramatic increase in rainfall, transforming the global climate into one that was far wetter and more humid. This shift is believed to have been triggered by volcanic activity as the supercontinent Pangaea began to break apart. This volcanism led to the formation of the Wrangellia Large Igneous Province, now found in northwest North America, from Vancouver Island to the Wrangell Mountains in Alaska and Canada. The volcanic activity released vast amounts of greenhouse gases, especially carbon dioxide, into the atmosphere. This spike in atmospheric CO2 caused global temperatures to rise. As the Earth's surface warmed, the water cycle intensified. More evaporation led to more water vapor in the atmosphere, which in turn led to increased rainfall. This also altered other climatic systems, including wind patterns and atmospheric pressure. The consequences of this increased rainfall were profound. A positive feedback loop ensued. More rain encouraged the expansion of lush vegetation across the continents. Ferns, mosses, and other water-dependent plants thrived, while conifers and other drought-tolerant species changed their distribution, though they remained common in some areas. Many terrestrial animals that had survived the arid conditions of the early Triassic began to decline, while newer groups, better adapted to wetter conditions, began to flourish. Most notably, this was the turning point for the dinosaurs. Although they had existed for around 10 million years, they had remained low in diversity. The wetter climate of the Carnian Pluvial episode gave them the ecological opportunity to diversify rapidly. And it wasn't just the dinosaurs. The earliest known pterosaur appeared around 228 million years ago, just after the Carnian Pluvial episode, and crocodilomorphs also began to diversify at this time. This expansion came at the expense of earlier archosaur lineages and the temnospondyls, both of which declined. Synapsids, such as the dicynodonts, also dwindled, although early mammalia forms continued to persist in their small, nocturnal insectivorous roles. The effects of the Carnian Pluvial episode weren't limited to the land. The oceans were also deeply affected by both the increased rainfall and the continued volcanic activity. The recovering reef ecosystems collapsed once again, a recurring theme in Earth's history, highlighting just how fragile reef ecosystems can be. As carbon dioxide dissolved into ocean water, it formed carbonic acid, causing ocean acidification. This process likely also led to acid rain, impacting terrestrial ecosystems as well. Acidification, combined with low oxygen levels and possibly euxinia, an excess of toxic hydrogen sulfide, further disrupted marine environments. These conditions primarily impacted already declining marine lineages. While several families of ammonoids disappeared, others rose to fill their ecological niches, making this more of a faunal turnover than a mass extinction. Conodonts, already in decline since the end Permian extinction, suffered further losses. Bivalves and brachiopods were also significantly affected, though both groups survive to this day. On the other hand, marine reptiles like ichthyosaurs and plesiosaurs seemed largely unbothered by the upheaval. These groups took advantage of the ecological gaps left by the more sensitive species, increasing in abundance and diversity. While the Triassic is often overshadowed by the more famous Jurassic and Cretaceous periods, the Carnian Pluvial episode was a turning point. It set the stage for the Mesozoic era's most iconic animals, dinosaurs, pterosaurs, and marine reptiles, by clearing the ecological path for them to rise to dominance. Before getting to the Jurassic period, we have one final event during the Triassic, and it was a large one. The Triassic-Jurassic extinction event was one of the big five mass extinctions, ranked fourth in severity. Occurring around 201 million years ago, it signified the boundary between the Triassic and Jurassic periods. The Triassic had already witnessed a series of climate shifts and volcanic events, and the Triassic-Jurassic extinction was the culmination of this instability, driven largely by another volcanic eruption. This time, the Central Atlantic Magmatic Province, one of the largest igneous provinces, was the culprit. Located in central Pangaea during the time of the supercontinent, its effects are now scattered across the Atlantic Ocean, with deposits in areas like northwestern Africa, southwestern Europe, northeastern South America, and southeastern North America. The eruption released massive amounts of greenhouse gases into the atmosphere, exacerbating previous warming, ocean acidification, and oxygen depletion, along with possible acid rain and widespread wildfires. Corals, many of which had already been decimated in the end Permian extinction, suffered another die-off. After the Triassic-Jurassic extinction, corals would vanish from the fossil record for several million years, although they persisted in very small numbers. They would eventually recover, but only in the middle to late Jurassic, and even then, coral reefs would be much simpler than before the extinction event. Marine reptiles were divided in their response to the extinction. Ichthyosaurs, which were already thriving, faced no disruption and would continue to diversify into the Jurassic, solidifying their role as the top predators. Plesiosaurs also performed well, surviving the extinction, but other marine reptiles like nothosaurs, thalattosaurs, and placodonts disappeared. The reason for this disparity lies in their ecological niches. Plesiosaurs and ichthyosaurs were generalist predators with a wide range of habitat tolerance, while the more specialized marine reptiles required specific habitats and prey. For example, nothosaurs depended on shallow coastal waters, possibly coral reefs, which had completely collapsed during the event. Similarly, placodonts, which specialized in feeding on shelled prey like bivalves, suffered because of the depletion of those species. On land, the extinction was catastrophic for many groups. Archosaurs, which had competed with the early dinosaurs, suffered major losses. Atosaurs, heavily armored herbivores resembling ankylosaurs, and Rawasuchians, large predatory crocodile-like reptiles, both went extinct, creating space for dinosaurs to dominate. Other crocodile relatives, like phytosaurs and ornithosuchids, also vanished. Temnospondyls had been in decline for much of the Permian and Triassic, and this extinction event nearly wiped them out entirely. A few species survived into the Jurassic, like Keratobrachiops, but they would never recover, disappearing completely by the middle of the Jurassic period. Pterosaurs, which had emerged in the late Triassic, also experienced a bottleneck during this extinction, with many species disappearing. However, the survivors were able to capitalize on newly opened ecological niches. Their ability to fly allowed them to rapidly diversify in the aftermath of the extinction, similar to how the ammonoids rebounded. The synapsids, which included many of the remaining lineages of mammal-like reptiles, were nearly wiped out, with only the mammalia forms, the earliest ancestors of mammals, surviving the extinction. As these groups declined, the stage was set for the rise of new life forms. The most notable winners were the dinosaurs, which would go on to dominate the next two periods. Unlike their modern descendants, the crocodiles, the crocodilomorphs of the time were small and fast. This made them highly adaptable, enabling them to survive the event and flourish in the aftermath. Another group that thrived was the lepidosaurs, which included the ancestors of modern-day lizards, snakes, and tuatara. Though a small group at the time, they managed to survive the extinction and would diversify in the Jurassic. The Triassic-Jurassic extinction event was a pivotal moment in Earth's history. While it brought an end to many ancient lineages, it also cleared the ecological slate, allowing new groups to rise and flourish. In many ways, this extinction didn't just close the chapter on the Triassic, it set the stage for the dramatic evolutionary stories that would unfold in the Jurassic. The dominance of dinosaurs, the expansion of marine reptiles, and the quiet persistence of early mammals and lepidosaurs all trace their roots back to this moment of global upheaval. I hope you enjoyed this video. In the next installment of our mass extinction series, we'll enter the Jurassic Period, the true beginning of the age of dinosaurs. Next week, we'll return to one of my channel's more standard videos, with a deep dive into some strange African bovids. Thank you for watching, and don't forget to share your thoughts in the comments below.